It's a great pleasure to introduce to you Rodolfo Aguilar from IMSA University of Miami. That's going to speak us about Calabi-Yau versus Calabi-Yau threefolds. Please, Rodolfo.
Thanks for the introduction. Is it working? So thanks for the invitation. I'll try to see if I can make it work. So what I'm going to tell is going to be a comparison between some properties of Calabi-Yau threefolds and low Calabi-Yau threefolds. And this is doing work with Martin and Griffiths. So let me start. Let me just recall you that a Calabi-Yau threefold is going to be a smooth projective threefold. I'm just going to ask that the canonical bundle is going to be trivial. So I'm not going to ask anything about fundamental group or I'm just focus on the threefold case. So what I'm going to use is that the existence of a holomorphic volume form, and then I'm going to multiply some sheaves, some cohomological spaces with this trivial line bundle, and then I'm going to use this holomorphic form to spread it in a different way. And I want also to do this in the quasi-projective setting. So a low Calabi-Yau threefold is a smooth quasi-projective threefold, such that if you have a smooth projective completion, let's call it X bar, such that the divisor is simple normal crossing, then you have that the minus the canonical divisor to this divisor is linearly equivalent to the trivial and divisor on the completion. So the example that I will be considering the most is I will consider X bar to be a Fano threefold. So in this case, this minus Kx is going to be ample. And I'm going to consider a smooth K3 on this anti-canonical divisor. And then I'm just going to remove this K3 from the Fano. And this is going to be a low Calabi-Yau threefold that I will be interested in.
So you mean plus K?
That's correct. Yeah, right. Cannot. So the idea is the following. We will actually consider variation of compact Calabi-Yaus, and we will call this the absolute case. And I will also consider the variation of pairs as in the second case here. But I want to have y fixed. So in most of the properties that I will explain today, we are fixing the boundary. We will be deforming the threefold of the boundary y is going to be fixed. We will call this the relative case. For example, we can start by noting that the tangent space to the space of deformations, so the Greenwich space, the universal space of deformation, this is controlled by h1 of x omega x squared. So in the classical case, in the absolute case, this is due to Dukomolov Todorov, and in the relative case, this was worked by Bovio. So let me just recall in the Calabi-Yau case, this is the space controlling the deformation. So as I was saying, we will multiply here by the OX. In this case, this is A of X. And we are using the volume form that in this case is this just to have this isomorphism, just to identify this group. So we are using a volume form that in this case is unique up to a constant. And in the Calabi-Yau case, the low Calabi-Yau case, the tangent vectors that are controlling the deformations of the pair are those tangent vectors that are tangent to y. But actually, we want to fix y. So if we want to fix, we actually consider the tangent vectors that are bounding on this y, and this is the group that that is controlling the deformations of these pairs. Now we are using that y is going to be on this minus kfx. We are having an isomorphism like this. So I'm using the notation here for a value, and this x should be x bar. So this is the first analogy that we have between the absolute case and the relative case. The tangent space to the deformation can be seen to be this group. So I have some remark that if this can be seen as unobstructedness of the module space, but if we consider y to be singular, to be, let's say, not as smooth as I will be considering in this talk, so the deformation can be obstructed. This is a result of Pelton, but I'm not going to talk about this. So now let me just go now to the cubic case. I will have some cubic forms, and in the Calabi-Yau case, I will start by considering a Kuranishi family. It's a universal family of deformations. Calabi-Yau, this is smooth projective, and I will take a point P in this Kuranishi in the base. Now, if I take a look at the tangent space, from what I said before, this is H1 Tx, but this is actually going to be isomorphic by using this volume form to H21 of X. Now, we can consider the variation of Hodge structures of the elements of the family here, and we will have a module space of these variations, and this is what is called the classifying space. And we have a map, the so-called the period map, that is going from the base of this family to this classifying space. Now, every time that we take a tangent vector in this family, we have a map that is going to be actually the derivative of the period map that is given by the Collider Spencer, and this is known as transversality. That is telling you that when you have a group like this, it will decrease by 1 in the first coordinate and it will increase by 1 in the second coordinate. So we are interested in this Calabi-Yau threefold. So we will start with H330, that these are the global sections of this global section of KFX. And now we will take one tangent vector, and by this property, we will go to H21. So then we take another tangent vector, we apply that again, and we will go to H12, and then we take a third tangent vector, and we will go to H03. So we will obtain a map from S3 of H1 of Tx to the symmetric second power of the dual of H0 of K of X. But we are in the Calabi-Yau case, so this is going to be C, and we are obtaining a cube form just by taking the iterations of the applications of the derivative of the period mapping. And so this is the so-called Yukawa Griffiths cubic, and we are in the Calabi-Yau case. If you consider the mirror of the Calabi-Yau threefold, there should exist a cubic form of this expected that you can write it in this form, and this is encoding enumerative properties of the original threefold. So I'm not really going to talk about this, but I expect something like this should happen also in the logarithmic case. So now let me go to the logarithmic case. The notation is as follows. So we take X to be a smooth projective Fano threefold, and we are taking Y to be, as I was telling you before, this is a K threefold, and on the anti-canonical linear system. So now I'm going to look at this as an element of this group. So I have the third anti-symmetric power of the tangent space. So we have a map as follows. So if we fix this y, if we take an element in H21, we can multiply the multiplication here will induce a map in homology, and we are going to contract these two forms with these two vector fields that we have here, and we will arrive to H1 of Tx. So by choosing this y, we obtain this map. And now, if we arrive to H1 of Tx, I showed you that if we consider again a Kuranishi family with this kind of log Calabi-Yau threefolds, also the tangent space to the base is going to be this group, and we can consider the same situation as in the absolute case. There will exist something called a period map. This time we have a mixed fault structure, and we will have also the Griffiths transversality in this case. So we take some tangent vector, and this is going to decrease the first coordinate by 1, and it will increase the second coordinate by 1. We can write this as a symmetric product. And now we can take together the two maps. So the first one was induced by fixing a y in the anti-canonical linear system. And now I'm writing this in the other side. So I put it here as a dual. So the first one is just induced by multiplication. But the second one, I'm applying this derivative of the period map, and I'm mapping to this. So in this way, every time I fix a y on the anti-canonical linear system, I will obtain a cubic on S3 of H1 omega 2 dual, and this will also give a cubic. So if you compare with the absolute case, just by equalizing this, we will obtain a very similar cubic, but this time, of course, it will depend on that we fix the boundary, that we fix y. Now, the result that I want to present is that if you have a cubic threefold and you fix y in this anti-canonical divisor, you should assume that both of them are generated. Then the cubic cy is smooth. So for this, we use the Jacobian ring. We express all the groups that are entering the definition in terms of the Jacobian ring, and we will see actually with the help of the computer that for generic and using some criterion for smoothness, that this is going to be smooth. So we should be careful because, for example, if we consider what we call the Fermat pair, that is, if you consider X to be the Fermat cubic threefold, and Y is going to be given by an intersection of equation of degree 3 and equation of degree 2. And this equation of degree 2 is also a Fermat type of equation. Then the cubic for this pair is going to be 0. It will factor actually by the Jacobian ideal, and so by the identification that we have here, it's going to be 0. So naive question that we could ask is, in the classical case, this cubic is related to mirror symmetry and enumerative questions. So the first question should be, is this cubic that we are obtaining here also related to some enumerative type of questions? We don't have an answer to this, but I expect that it should be the case. Any questions? So now I will talk about curves. So let me recall briefly, probably most of you know the definition of Abel-Jacobi math. So I will take X to be a smooth projective threefold, and its intermediate Jacobian is going to be the following compact tori. So you take the third homology of the threefold, and then you quotient by the second part of the filtration, of the Hodge filtration, and the integer part of the H3. And this can also be seen as the functionals acting on this part and quotiented by the third homology. So now we will denote by this the codimensions two cycles that are homologous to 0, and the Abel-Jacobi map is going to be defined on these cycles that I will define as follows. So if you take a cycle that is homologous to 0, I will take a chain of free chain that bounds, and I will integrate these test forms on this chain, and this is going to be the definition of Abel-Jacobi. Now we can consider algebraic deformations of the curves C inside the smooth projective threefold, and this is going to give me an algebraic parameter space, so so-called Hilbert space, and we can consider also let's call the algebraic differential of Abel-Jacobi, and the tangent space. So this parameter space is going to be H0 of the normal bundle of C on X, and the differential of this Abel-Jacobi can be seen as the follows. So can be seen as follows. So here we will use that the differential of the Abel-Jacobi is given by something in this form. So you take the tangent space of this parameter that is going to be H0, and you map to the algebraic part of the intermediate Jacobian, that is, you're going to land on H through 1x. So this keep up here. So this is the dual of the tangent space of the deformation that I was telling you before. So now I'm going to be interested on deformations of pairs. So we can ask, if you deform a Fano, Calabi-Yau threefold, and you have a curve, let's say a smooth curve inside it, does this curve deform when you deform the threefold? And this will be also the same question for the logarithmic case. And it happens actually that the obstruction to deform this pair is measured by the differential of the Abel-Jacobi. So this was known by Clemens in the projective case, and the main result of this talk is that we can also obtain this in the relative case. It's going to be, we're going to need much more notation, but this is basically the result that I'm going to present. So now, let me introduce more notation. So once again, we're in the absolute case. So X is going to be a Calabi-Yau threefold. We will consider a smooth curve. So now, because the canonical bundle is trivial, we will have this equality. This H0 of the normal bundle of the curve is going to be isomorphic to H1 of the normal bundle. And to compute the obstruction to the form C with X, we will have some exact sequence, and we will have a long exact sequence of cohomology associated with this. So this is basically the normal, the tangent vectors that are tangent to C, but we obtain a sequence like this. So the most important part of this sequence is that we have a map from H1 of Tx going to H1 of the normal bundle of C and X. So this one, I can write it as H1 of omega 2 of X as by multiplying by the holomorphic volume form. And this one is going to be dual as I wrote here. to this H0. So if you remember the what I told you in the last page, this looks like the dual of Abel-Jacobi. And so a proposition, you can actually show that this delta is dual to the differential of Abel-Jacobi. So now the corollary is what I was saying. If you take a direction in the tangent space of the universal family of deformations, the curves that the forms of first order in the direction of theta are those that satisfy that they vanish with the dual of the differential of the Abel-Jacobi map. So now this is the result that we want to obtain in the relative case. Yes. Smooth. The smooth curve on Calabi-Yau threefold.
What's the subscript on the capital T, H1 of T
H1 of Tx, yes, always.
of X?
The tangent space
Okay,
of X. Can you repeat your question, sir? The canonical one is visible also? One. First one.
I think it's actually 0.
About this one. H0 to the normal bundle of C to the global. This one, if this is self duality, this is what you're asking. I think it's more complicated. I think it's not only self duality. But with the smooth should be okay. Sorry, I think we can discuss it. I don't think I'm getting there. So let me go to the relative case. So in the relative case, we are going to introduce the parameter space of curves. So now X is going to be again a smooth projective Fano threefold, and Z is going to be the parameter space of curves of degree D. So this degree is the anti-canonical degree. And we are basically taking C to be smooth. We are also considering Y to be an anti-canonical surface. And so every time we take a small c on Z, this is going to represent a curve. So we will have C of Z that is a curve inside X. And this curve will intersect Y in the points. Let's assume that the intersection is transverse. And so in this form, we will have associated to, let's say, the smooth part of the curves set here, a point on the symmetric product of Y. Now, for simplicity, everything will be smooth and everything will be transverse here. So note that this YD is a hypercolor manifold, and I will denote the true form by C in this form. So now, Juliet and Manivel prove that the image of this set is a Lagrangian submanifold of this Y to the D. And actually, there is a theorem due to Juliet and Manivel in the prime Fano triple case, and Marcus proved it in general, that the relative intermediate fibration, Jacobian fibration, is a Lagrangian fibration, and that G is holomorphically symplectic. So let me explain this result. So you have the universal family of the formations of the pair of the Fano threefold and Y. Well, Y is keep it, is fixed. So now for every point, you have the Fano and you have y that is fixed. Now, so this, you can associate the intermediate Jacobian of P, and you will have, this is the relative intermediate vibration. So now, this vibration is going to be a Lagrangian vibration, and this is going to be a holomorphically symplectic. So now, this is the relative analogous of a result of Donagi and Marmon. They show in the absolute case that if you have a complete family of Calabi-Yau threefolds, so the relative intermediate Jacobian, you have to take a C star bundle over M. So this is called a family of gauge Calabi-Yau threefolds. So this is going to be a Lagrangian vibration. And this J is going to have a holomorphic symplectic structure. So it's really the analogous of this result, just that in the relative case, the gauge disappears. Thoughts for questions, if there is any? So now let me continue introducing more notation. So we have a relative complex situation here. So we have for every point, we have the parameter space of curves inside XB, and this will map to Y, to the symmetric power of Y, and we also have the relative Jacobian vibration. And now, let me denote by alpha a map that is mapping from the tangent space of Z to the tangent space of Y to the D. And so this is basically the derivative of the map that I considered before. And we have a vector, it intersects Y and D points. This is the derivative of this map. But we will also have some map of beta given by deformations of this pair keeping Y fixed. And so the tangent space, so this beta is going to be H1 of omega S2, and you are mapping as well, so this YD. And this will actually map to the normal bundle of the image of this FZ. So we will have two maps here. One that is going to the tangent space of the image of this parameter space, and the other one is mapping to the normal bundle. And so the main result is that you can use the two form here to evaluate these two orthonormal vectors, and this is going to be just given by the differential of the Abel-Jacobi map and the coupling of these groups. So let me read it. So you will take a vector field on the tangent, a vector on the tangent space of Z, and you will also take another vector on the tangent space of the universal space of deformation. In this case, this is H1 of omega 2. And you will consider the symplectic form on Y of D. So we will have that if you plug in by the maps that we defined before, you send it to Y of D, one by alpha and the other one by beta. This is going to be equal to the pair of the differential of the Abel-Jacobi map, and this pair is just given by this tensor product of dual groups. So a corollary of this result is really the analogous of the result that we had in the absolute case. So if we consider the universal family of deformations of this final threefold. Now we are keeping fixed y. We will have an open subset of this vector space, and we will have an exact sequence like this. We have the normal bundle of the curve inside X, and we will have the normal bundle of the curve inside the p variation. And now you have also the normal bundle of X inside the Kuranishi family. And this is going to be identified with the tangent space of the base multiplied by this structure sheet. So if you take the long exact sequence associated to this, you will obtain a map as follows. So this is going to be from H0 here, and we obtain delta, and it's mapping to H1 of the normal bundle. And now this time, we won't have the whole H0 as we had before. So we have now a subgroup. So this is going to be mapping AFX, mapping to H0 actually in an objective way. And so we have a part of the Abel-Jacobi morphism. So the corollary is that the pair C of X, the curve, and the final threefold keeping the boundary y fixed, they form freely. So first order in the direction, in this direction, you can only the dual of the Abel-Jacobi map is 0. So is this clear? Formulation and so now let me give you a sketch of the proof. Some ideas that we use it. So the first one is I will give the ideas for the proof of the proposition of Gillick-Manigel that the image of this parameter space of curves is the Lagrangian submanifold. So if you consider the holomorphic 2 form on the K3 surface, you can lift it to a 3 form having poles on Y on the threefold X. So now the tangent space at a point set in the parameter space of curves is the normal bundle. So we can do two things with this. We have the 2 form, we lift it to the threefold, and in the threefold we have the curve. So we can do it in two ways. We can restrict the 3 form first to Y and then to the Y intersected with the curve, or we can restrict the 3 form to the curve and then intersect with Y. And so basically we're going to obtain a commutative diagram, and in one way we are obtaining that is going to be the residue and then the Gießen map, and this is going to be 0. And then you need to see that it commutes and that you will obtain the same in the other way. And so it will tell you that the restriction is going to be 0. So let me just remark what I said. So we have the 3 form having poles on Y. So we can restrict to Y and then to the intersection with the curve, or we can restrict to C and then the intersection with Y. So let me do the second one. So we have this element here. So now if you restrict to the curve, of course you can only have one form on the curve, and the other part of the 3 form is going to go to the normal bundle. And I'm writing here the normal bundle, so this omega 2 is just the dual of this. And so now we take residues on the curve, and then we take the Gießen map here. And so this composition is going to be 0, and you will have to see that the diagram that you obtain also here, you obtain the same result, and so this is 0. And this is how you prove that the image of the parameter space is going to be Lagrangian in this Y and Q. So now, for the theorem, we want to do something similar. We want to lift the two form on Y, so we are deforming a Fano threefold, but we are keeping fixed the boundary. So we can lift it in the relative bundle, but we want to really have a form that is defined on every direction. So if we have this, we could apply a similar argument to this, but actually we will have an obstruction. So an obstruction to lift this two form is going to be on the differential of the period map, of the mixed period map. But the solution is that you can actually lift this form to a C infinity form. So this is going to be a C infinity form that lives in the total space of the Granici deformation, and this is going to have poles on Y and also on a small neighborhood of the fixed point on the base, on the Granici base. So now, doing this, we know that if you restrict fiber-wise, this is going to be Lagrangian, so this form is going to be 0, and it will lie in the kernel of this map. So you have a tangent space, you have also the tangent space on the vertical direction. When you are considering the family of curves inside some fixed Fano threefold, but you can also see this as a family when we vary. And so by this condition that this is 0, and you will see that we can have a part of this lift landing in this sheet. So we're in the Granici family, and the normal bundle of set inside the family of parameter spaces of curves. This is going to be just this cohomological, this H21 of X multiplied by the structure shape of the base. So now we need to do the same. We need to restrict first in one direction, and then we will have a commutative diagram, and then we will have also the restriction in the other direction, and we will have to identify the maps, and then we will see that we are obtaining in one way the two form, and in the other way that we are obtaining the differential of the Abel-Jacobi. This is basically, we have something like this, and you can identify that you will have this formula. So it's based on the idea of this proposition, but you will have much more details. So this is what we have in the relative case. So we can ask what's next, what else we can do, what kind of analogies we can find. So we can ask if we can define something like relative Abel-Jacobi maps. So we have Abel-Jacobi in the Calabi-Yau case, and I will have some slides about Fleming's conjecture. So we can ask if we can obtain something like this also in the relative place. Second point, we can also ask if some relation with the Gromov-Witten invariance can be shown. So let me just continue. I will comment after this. So if you consider the absolute case, let X inside P4 be a general quintic hypersurface. So a result of Griffiths is that it has only a finite number of lines, and that the Abel-Jacobi map in the difference of this line is not a torsion point in the intermediate Jacobian. So now we have some conjectures of plainness in this Calabi-Yau case. So let's consider X be a smooth projective threefold with K of X trivial, and we consider F to be a map from P1 to X. Let's say it's locally immersive. So the first conjecture is that the infinitesimal Abel-Jacobi map is injective. We have a second conjecture that says that for X generic, X has only isolated rational curves with O-1 plus O-1 bundle. And then the generic quintic threefold admits only a finite number of rational curves of each degree. We can ask the following questions that Griffiths we were discussing. So is really the Abel-Jacobi map injected on the set of rational curves? Not only its differential, probably, of course, clearance have this in mind. And if this were true, it will have some implications that actually these are theorem now proved by Clemens, Malzahn, and some other people, that the image by the Abel-Jacobi map of the rational curves is a non-finitely generated discrete groups. So we can ask if we have something similar to this in the relative case. So first of all, we need to define what a relative Abel-Jacobi map is. So the cycles in the relative cases are more difficult because the integral that you use to evaluate them usually will go to infinity. So you don't have a way to control this, and you will have to choose which kind of cycles can you integrate. So another thing is that you will probably have to use more technology. So I think Marker has worked on this. He can define relative Abel-Jacobi. And so the next question is if we can have something like this also in the relative case. So if we can, using this relative Abel-Jacobi map, and we consider rational curves on the final threefold, let's say intersecting transversally on the same set of points, the boundary is the image by this Lewis relative Abel-Jacobi map injected on this kind of curves. And also, I think we can ask what kind of conditions of the curves intersecting the boundary divisor you should impose in order to have only a finite number of curves in the log Calabi-Yau case. So I think these are questions that I'd like to explore later and try to see what can be done to compare that further the absolute Calabi-Yau case and the relative Calabi-Yau case. So I'm a bit earlier, but I will stop here. Thank you.